Hello, today's topic is drug antagonism. A drug is said to be antagonized when one drug interferes or inhibits, opposes the action of other. Okay, and we have some terminology that is intrinsic activity, which is usually deals with all these agonist, antagonist, and inverse antagonism reactions. So in antagonism, drug antagonism, there will be just affinity or it will form a reaction, but there is no intrinsic activity. This is very important. Antagonist will not have any activity. Okay, it will just bind and will produce no effect. The effect is zero. Unlike agonist, which will produce +1, inverse agonist will produce opposite action of agonist, that is -1. Likewise, the antagonist will produce an effect that is 0. Okay, partial agonist will produce a reaction which is in between 0 and +1. So these things are very important. So in antagonism, it is no activity, and it is usually a drug is said to be antagonized when one drug opposes or inhibits the action of other. And there are various types of antagonism which is very important. These types are chemical antagonism. We will study in detail in further slides. Physiological or functional antagonism it is called, and pharmacological antagonism, which is mainly at the receptor level. Okay, pharmacological antagonism is mainly at the receptor level. It is receptor mediated, and this pharmacological antagonism is of three types, that is reversible or competitive type of antagonism, irreversible, it is also called equilibrium antagonism, non-equilibrium antagonism, and non-competitive antagonism. So these are various type of drug antagonism. Types of antagonism we are studying in detail. Chemical antagonism, as the name suggests, there will be some chemical reaction or interaction between two drugs resulting in inactivation. Okay, so examples for this is chelating agent, that is BAL, okay, which is given in case of heavy metal poisoning like lead or mercury, and they form an inactive compounds which is easily excreted from the body. Okay, similarly antacids, which is given in case of gastritis, that will also chelate or neutralize the gastric acid by forming a compound. It will contain aluminium hydroxide and they will neutralize the gastric acid. So these are example of chemical antagonism. So physiological antagonism or functional antagonism means the function is affected. Whatever one drug, whatever function it is there, so it is opposed by the other. So they will not act on same site, they will act on different site or different receptors, but they produce opposite effects. Effects are very important here. Effect is hampered. So example is histamine. Okay, what is the effect of it? Histamine is they will produce hypotension and bronchospasm by histamine mediated release of histamine, right? So this is a normal action of histamine, but this effect is the opposite effect is produced by adrenaline. Okay, adrenaline by acting on adrenergic receptor beta 1, beta 2, beta 3, alpha 1, alpha 2, alpha 3. These are the receptors where adrenaline acts. By acting on all these receptors, the effect produced by adrenaline is bronchoconstriction and hypertension. Okay, this is the effect produced by adrenaline. They act on different receptors, but they produce different or opposing effect. One is producing constriction, one is producing dilation, something like that, right? So hypotension, this is because of vasodilation. Adrenaline will produce vascular constriction through alpha 1 mediated action, and then they produce hypertension. So this is the opposing effect. Similarly, on blood glucose level, insulin and glucagon also have opposite effect. They also act on different receptor. Moving on to the pharmacological antagonism, which is very important. The first one is reversible or competitive antagonism. Okay, so in competitive antagonism, as the name suggests, the agonist and the antagonist will compete for the receptor. They will compete for the same receptor. The agonist and antagonist will compete for the same receptor. So if you want to overcome the action of antagonist, so you can increase the dose. Okay, this is one important thing which you can do in case of poisons. Example is D-tuberculin, which is an antagonist at the neuromuscular junction. The effect of D-tuberculin can be overcome by increasing the concentration of acetylcholine at the nicotinic receptors. Okay. In case of neuromuscular, that is NM receptors. So this is one good example. And in case of curization, for decurization we give acetylcholine analogs. So one more important example for competitive antagonism is same acetylcholine and atropine. Acetylcholine is an agonist and atropine is an antagonist. So these two are all, this is at the muscarinic receptor, where that is at the nicotinic receptor. Okay. So these things. And here you also should remember a few important points. The dose response curve shifts here in the right side. Okay. So this is a dose response curve, and this is obtained by drawing or by plotting the doses in log doses in the y-axis and response in the x-axis. Okay, so this is the dose. So 0.1, this is the response. 1, this is the response. Okay, likewise with response we will usually plot, you will keep a dot, and then if you join, so this will be the curve. Okay, this is how it is obtained. So this indicates the response. So normally this is the response in an agonist when you give. So this is the response. Say you have given okay, what is here? Okay, you have given acetylcholine. Probably this is, if you want to imagine, so this is the muscle contraction. So with increasing the dose, the contraction also increases, and after a level there will be a plateau level, right? So this is what is mentioned here. Likewise, this is the normal dose response curve. With increasing dose, what is the response? In the presence of antagonist, okay, in the presence of antagonist, the dose response curve shifts to right, meaning the dose of drug which is required to produce the desired effect will reduce. So what has happened here? See, with 1 milligram, the response seen here was up to 40%. See, this is 50% of response. See, this is, say, around 50%, 40 to 50% responses produced at whatever unit dose. But whereas in here, in the presence of antagonist, the response produces so less, it is less than 0 with 1 unit of drug, right? With 10 units, see, similarly, there is decrease in the response. When this is the response in only when you give agonist, and this is the response when an agonist is given in the presence of antagonist. Okay, understanding? The response is decreasing in the presence of antagonist. So that is why we say the dose response curve will shift to right. Okay, and as I have already mentioned, so in the presence of agonist, there is no the antagonist has affinity to the receptor, but there is no intrinsic activity. Activity is 0, that is, there is no response. Moving on to the next type of antagonism, that is irreversible antagonism or non-equilibrium antagonism, it is also called. Okay, in here what happens, the antagonist will bind to the receptor so firmly with a covalent bond so that it cannot be dissociated, or it will dissociate very, very slow, or it will not dissociate at all. Covalent bond, as we all know, it is a very strong bond, right? So it is very difficult to dissociate. So that is what happens. So that the agonist is now unable to reduce receptor occupancy by this antagonist. So the law of mass action, this cannot be applied here. That is, if you increase the dose of agonist, n number of agonists cannot come and occupy here because the bond is very strong, right? So it cannot release. So that is why it is called as irreversible. You cannot reverse the action of agonist. Okay, irreversible or non-equilibrium antagonist. Very, very important. And this blockage cannot be overcome with increasing dose, unlike competitive antagonism, and hence it is called as irreversible antagonism. And example is adrenaline and phenoxybenzamine. Phenoxybenzamine, we all know it is an irreversible antagonist at the alpha receptor, both alpha 1 and alpha 2. So adrenaline has action on all the receptor alpha 1, 2, beta 1, 2, 3. So in the presence of phenoxybenzamine, adrenaline cannot produce the effect because phenoxybenzamine has already occupied the alpha receptor irreversibly. So here also in the dose response curve, what we see, there will be progressive flattening of dose response curve like non-competitive, but the antagonism will be more compared to non-competitive antagonism. So this figure I have just put to just make you understand the receptor occupancy. See, this is the receptor okay here. So agonist will bind here and produce some action. But in case of competitive antagonism, see both agonist and antagonist. So this is these are the allosteric sites. So agonist and antagonist both will act on same receptor. They will compete. That is why it is called as competitive antagonism. This is how agonist bind, and antagonist it will bind like this. Okay, competitive antagonist. So if it is binding, it cannot bind here, and that is why there will be antagonism. Whereas non-competitive antagonism, which you will be studying in the next slide. So what happens there is, see, the agonist and the antagonist has different allosteric site. They will not compete for the same receptor. That is why it is called as non-competitive. So here it is a competitive antagonism. Okay. So non-competitive antagonism, you saw there. So they will block at the level of receptor effector linkage. Okay. But they bind to different site. Okay. So the receptor binding site is different. Receptor effector linkage. The next step, the intrinsic things which will happen later, that is blocked by non-competitive antagonism, which is beyond the receptor and not on the receptor level. Okay, this is what I was trying to explain you. So the dose response curve, what will happen? There will be flattening as well as rightward shifting of dose response curve. Okay, this is important question. Dose response curve will flatten and also rightward shift. Why? Very small responses produced. And moving on to the example, so verapamil, verapamil is a calcium channel blocker which will block the calcium during depolarization process, right? So and it will produce non-competitive antagonism, and it thereby antagonizes the effect of cardiac stimulants like isoprenaline and adrenaline, they are cardiac stimulants. It will inhibit the effect of these actions. So in this slide, you have the clear picture of differences between the competitive and non-competitive antagonism. It will also summarize these two type of antagonism. So the first difference is that they will bind, competitive will bind on the same receptor, whereas in non-competitive the agonist and the antagonist will bind on different they have different site for binding. In case of competitive antagonism, the antagonist will resemble the agonist resemble chemically with the agonist, whereas in case of non-competitive they do not resemble. And coming to the DRC, dose response curve, in both the cases they will shift on the right hand side, but in competitive there will be parallel rightward shift, whereas in case of non-competitive antagonism it is flattening of DRC. Okay, and in case of competitive antagonism the maximum response can be attained by increasing the dose of agonists. Okay, whereas here the maximum response is obtained by suppressed dose. So here in case of competitive agonist, the intensity of response depends on the concentration of both agonists and antagonists. Okay, both agonist and antagonist concentration it will depend on, but in case of non-competitive it will only depend on the concentration of antagonist. This is same as that of the previous point, but in case of response and intensity of response, maximum response. Examples for competitive antagonists, as we already have seen, acetylcholine and atropine, and also morphine is an naloxone is an antagonist of morphine. Non-competitive, we know it is on different sites, so good example is on GABA receptor, where diazepam and biquiculin have different allosteric site for binding. So very important this table for both for theory and for your MCQ. Hope you understood mainly this antagonism chapter. So these are few MCQs which is commonly asked. Non-competitive inhibitor of an enzyme will do what? It will increase Km, or it will decrease Km, or it will decrease maximum response, or it will increase Vmax. So what it will do? So you have to read back all the chapters and answer as mentioned in the next slide. Which of the following is true for receptor? So go in detail. So regarding the physiological antagonism, this is one question. Okay, thank you.